Welcome to online classes of physics for B.Sc 6th semester students. We shall discuss today the molecular physics, in which we shall discuss in detail the molecular spectra, molecular motions, and molecular energies. In the figure, it is observed that the interaction of radiation with the matter. So, if the electromagnetic radiation interacts with the rotation of the molecule, then that corresponds to rotational spectra, usually that is observed in the microwave region. If electromagnetic radiation interacts with the atoms, the vibrations of the atoms of the molecule, that corresponds to vibrational spectra, and that is observed usually in the infrared region of the electromagnetic spectrum. If the electromagnetic radiations interacts with the atoms of a molecule, then there is a change in the position of the electron from one orbit to another orbit. So that corresponds to electronic spectra. So that electronic spectra usually observed in the visible and ultraviolet region of the electromagnetic spectrum, and this energy corresponds to, that is, large number of available energy states that is strongly absorbed or emitted in the ultraviolet and visible region, and only small number of available states almost transparent. So that means if there is no available quantized energy levels matching to the quantum energies of the incident radiation, then that material will be transparent to that radiation. We shall we shall discuss the types of molecular motion. There are three types of molecular motion. One is translational motion, second one is rotational motion, and the third one is vibrational motion. The first one, the translational motion, as the name itself, there is a change in the position of the molecule from one place to another place. So that means the molecule changes its location in three-dimensional space. In gas phase, molecules are free to move from one place to another place and also have considerable translational motion. The rotational motion of the molecule corresponds to the rotation of a molecule about a fixed axis. The internal parts of the molecule rotating with the respect to the one another, and this corresponds to the rotational motion of the molecule. So the rotational motion is present in molecules both in gaseous phase as well as liquid phase. The vibrational molecular motion, the motion within the molecular motion that changes the shape of the molecule by means of stretching, bending, and rotation of bonds. Vibrations can be classified as asymmetric stretching and symmetric stretching and bending. So the three motions of a molecule are shown pictorially. The left side of the picture shows the vibrational motion, in which bending, symmetric stretching, and asymmetric stretching vibrations are shown, and at the center we have shown the rotation of a molecule about a fixed axis. And in the right side picture, the motion of a molecule from one position to another position, so that corresponds to translational motion of the molecule. The energy associated with the given segment of the spectrum is proportional to its frequency. The below equation describes this relationship, which provides the energy carried by photon of a given wavelength of radiation. The frequency, the velocity, and the wavelength of the electromagnetic radiation are related by an expression nu is equal to c by lambda, where nu is the frequency, c is the velocity of the electromagnetic radiation, and lambda is wavelength. The energy and electromagnetic frequency of the electromagnetic radiations are related by delta E is equal to h nu, where h is the Planck's constant, nu is the frequency of radiation, and E is the energy. Since h is constant, so this implies that E is directly proportional to nu. That means the frequency, more higher the frequency, higher will be the energy. The molecular energies, the energy corresponds to molecule are classified once again: the translational energy, rotational energy, and vibrational energy, and electronic energy. Due to the motion of the molecule from one place to another place, so that corresponds to the kinetic energy associated with the random motion of the molecule. It is absent in solids, whereas it is molecules in solids are held in a fixed position, exits liquids in a limited extent, and is only completely free in gases. The rotational energy, the rotational kinetic energy associated with the rotation about an axis is called as rotational energy. If you use the diatomic as a model, for a diatomic there are potentially 3 rotational degrees of freedom, that is, the molecule can rotate about x, y, and z axis. However, for diatoms and linear molecules, only 2 degrees of freedom are active. The rotation around the z axis is inactive because the position of the atoms in the space does not change during this rotation. For nonlinear molecules, all 3 degrees of freedom are active. The rotation of this diatomic molecule about x-axis and z-axis are shown in the figure, and also the y-axis is also present. So x-axis and y-axis rotation, that changes the position of the atoms of the molecule, whereas the rotation about the z-axis will not change the position of the atoms. Hence, only 2 degrees of freedom are present in case of rotational energy. So vibrational energy is the kinetic energy associated with the relative motion of the atoms which constitutes the molecule. So if you use a diatomic molecule which is shown in the figure, so that means atoms of a molecule vibrates, that is, they are stretching or contracting. So due to this stretching and contracts about their mean position, so that contributes the vibrational energy. The electronic energy of the electrons of the molecule arises due to the change in the positions of the electrons with respect to the nuclei in the molecule. Hence, if we assume that these different types of energy do not interact, then for good approximation, the internal energy of the molecule U is sum of translational energy, rotational energy, vibrational energy, and electronic energy. But mainly the molecular energy corresponds to rotational energy, vibrational energy, and electronic energy, which are discrete, because these have discrete energy levels. The molecular spectra, the transition between two energy states of a molecule as a result of absorption or emission of energy will give rise to spectral line. When a molecule suffers a transition from higher energy state with energy E to a lower energy state E dash, the difference in the energy is given by delta E is equal to E minus E dash is emitted as radiated of frequency nu and is given by nu is equal to E minus E dash divided by H. The molecular spectra. There are 3 basic types of optical spectra that we can observe for molecule. The first one is electronic or vibronic spectra, that is usually observed in the UV visible or near infrared spectra of the electromagnetic radiation. Vibrational rotational spectra usually observed in the IR region. Rotational spectra that is observed in the microwave region. In the picture, we observe that A and B are the two electronic states of a molecule. If there is a transition from one electronic state to another electronic state, that corresponds to electronic spectra. If there is a transition from one rotational level of the one vibrational level to the rotational levels of the another vibrational level, so that corresponds to the vibrational spectra. If there is a transition between rotational levels of the same vibrational level of the same electronic state, then that corresponds to rotational spectra, so that we are observing in the figure. So as you know, the study of interaction of electromagnetic waves and matter named as molecular spectroscopy. The spectra which is emitted by molecules containing two or more atoms is called as molecular spectra. Molecular spectra under low dispersion appear as a continuous bands, and for this reason they are often called as band spectra. The band has a sharp intense edge on one side called band head and gradually decreases in intensity towards the other side. With high resolving power instruments, band spectra are found to have threefold structure. Each band is seen to composed of large number of lines which are crowded together at a long wavelength side called bandhead, and as they recede from the bandhead, the lines become more widely spaced and also weaker. The lines, however, being so close together as to appear under low resolution like a continuous spectrum. There is a regular sequence in which several bands follow one another and thus constitutes a group of bands. These different groups of bands are quite close and thus because of their regular arrangement form a band system. Molecular spectra are also composed of monochromatic lines having approximately the same width. The name band spectra merely signifies the distinction from atomic spectra, the so called line spectra. So, we shall distinguish between the atomic and molecular spectra. The atomic spectra corresponds to interaction of electromagnetic waves with the atom, whereas molecular spectra corresponds to interaction of electromagnetic radiation with the molecules. Line spectra is due to the emission of electromagnetic radiation that corresponds to atomic spectra. Band spectra due to emission or absorption of electromagnetic radiation by molecules corresponds to molecular spectra. Sharp only one line due to emission of radiation due to electronic transition. In case of atomic spectra, the molecular spectra composed of band, and a band spectra consists of a sharp intense line crowded by large number of lines and going away from the band head, the lines widely spaced. Line spectra due to transition of the electron, whereas band spectra is due to rotation, vibration of atoms of a molecule and electronic transition. This atomic spectra used to study the nature of elements, whereas the molecular spectra used to study the structure of molecules and composition of elements. And in this figure, the change in the spin of the nucleus corresponds to NMR spectra, and the change in the spin of the electron corresponds to ESR spectra. The rotation of the molecule corresponds to microwave, which is observed in the microwave region, so that corresponds to rotational spectra. The vibrations of the atoms of the molecule, that is bending, stretching, and asymmetric stretching and symmetric stretching, and also the vibrations, that corresponds to vibrational spectra usually observed in the infrared region. The change in the position of the electron from the nucleus of the atom in the various orbits of the electron, that corresponds to electronic spectra, which is observed in the visible and ultraviolet region of the electromagnetic spectrum. The different regions of the spectrum are explained in detail. So, that is radio frequency region, microwave region, visible and ultraviolet region, and X-ray regions are in detail that are explained, and their frequencies as well as the wavelengths are also given, and what spectra that corresponds to these regions are also discussed in detail. Molecular spectra is usually fall into three groups, that is far infrared spectroscopy and visible and ultraviolet spectroscopy, and also the third one is infrared spectroscopy. The energy other than translational is essentially of three kinds, namely electronic, vibrational, and rotational, which are all quantized. That means the electronic, vibrational, and rotational energies are quantized. The transition between two energy states of a molecule as a result of absorption and emission of energy will give rise to the spectral line in the spectrum. So, this figure shows the molecular spectra, that is a band spectra, the sharp line that corresponds to band head, and as you recede from the band head, the intensity of that lines that decreases, and the lines are widely spaced. So, next we shall start with the rotational spectroscopy.